Alright, today let's have a look at the third topic in this course. We're going to have a look at the congruent triangles. Okay, first of all, let's have a look at a brief review of the concept of congruent figures. So by definition, two figures are congruent if they are exactly the same. In other words, we can slide, spin, or flip one figure so that it's exactly on top of the other figure. Any questions? Concept is pretty straightforward, right? I'll give you some examples. For example, this trapezoid is exactly the same with the one on the right, because when you flip, turn, rotate, then translate, one is exactly on top of the other, right? Note that the corresponding points are labeled with the same color here. So this point is corresponding with this point is with this point with this point here, and this point is corresponding with that point. And similarly, let's have a look at another example. These two triangles are exactly the same with each other, so they are also congruent figures, right? And here are some other examples. And note that we have some special property of congruent figures. So let's have a look at their properties first. First of all, corresponding parts of congruent triangles are congruent, which means exactly the same, or abbreviated as CPCTC. And in this course, we'll focus on studying the congruent triangles only. So for the following discussion, we'll only talk about congruent triangles, okay? For example, these two triangles are congruent. Usually we use this symbol to denote the congruent triangles. Here, a triangle DEF is congruent with triangle QPR. Usually, congruent triangles are named by listing their vertices in corresponding order, okay? So because here, D is corresponding with Q, E is corresponding with P, F is corresponding with R. Therefore, we list the three vertices in this order, okay? Usually, we'll list each of the congruent triangles in this way. And then you can see which point is congruent with the other point, right? Any questions? Again, the property is pretty straightforward, right? Congruent parts of the congruent triangles are also congruent, CPCTC. And the problem is that how can we determine if two triangles are congruent? We have a series of testing series. So let's have a look at these series. First, if two sides and the angle between them in one triangle are congruent to the corresponding parts in another triangle, then the triangles are congruent. For example, let's see the figures on the left. If we have a triangle AMN, another triangle OJB, so these little strokes here means the corresponding sides are equal, right? AN equals OB, AM equals OJ, and angle in between the two sides, angle NAM equals angle BOJ. In such a way, by the testing theorem 1, SAS means side angle side. We have triangle NAM is congruent with triangle BOJ. Okay, this is called the testing theorem 1, SAS. So the problem is, can you prove this is actually true? So are you clear with the testing theorem 1? Okay, think about this question here. Let's try to prove the theorem SAS. So given two triangles here, ABC and DEF, given AB equals DE, AC equals DF, and angle in between are also congruent, can you prove triangle ABC is actually congruent with triangle DEF? I'll give you 2 minutes to think about this question, okay? Remember, this is a theory. Theory needs proofs, right? So how can we do this? I'll give you 2 minutes to think about that, and then we'll have a look at the solution together, okay? You can compare your solution with mine. Actually, there are more than one methods you can prove this. All right, let's have a look at the solution together. So the key to prove two figures are congruent with each other is when you translate one figure to the other, each element of one figure should be exactly on top of the other figure, right? So here, okay, I'll write it here, proof. We can first put the point A on D and put the line AB on the line DE, right? This is possible, right? If you drag the point A on D and then put line AB is on line D, this is possible, right? Because we only fix one point here and put one line on top of the other one. Then next, because AB equals DE, we have point B must coincide with point E, right? Can you follow me? Because AB equals D, then B must coincide with point E. Therefore, we know the segment AB must coincide with the segment DE, right? So this proves one segment is on top of the other. And then let's have a look at the other two segments. Then because we have angle A equals angle D, then we know the line AC must coincide with the line DF, right? Because when two angles are exactly the same, they must share the same size, right? So if one of the sides AB is on top of D, then the other side AC must be on top of DF, which means AC coincides with DF, right? Can you follow me? And because segment AC equals DF, this is also known to us, we know point C must coincide with the point F, right? Therefore, we know the segment AC coincides with DF, right? Also, we know B is on top of E, C is on top of F. Therefore, BC, segment BC coincides with EF. And then we proved every element of triangle ABC is on top of every element on triangle DEF. Therefore, we know triangle ABC must be congruent with triangle DEF, right? Again, the conclusion seems straightforward, seems very simple, but you still need to prove this statement is true. Any statement you made in geometry, you need to prove that. Other than the fundamental axioms, okay? All right, have you finished? Okay, if you haven't finished, just give me a shout, okay? I'll wait for you for some more time. Otherwise, let's make a summary. So basically, this theorem tells us if two sides and angle between them in one triangle are congruent to the other one, to the corresponding parts in another triangle, then the triangles are congruent, which is abbreviated as SAS, side, angle, side, okay? And then we have proved this theorem like this. And well, after this class, you can think of, are there any other ways you can prove it? Okay, there are more than one way, at least, probably 10 different ways we can prove this. Okay, then let's use this testing theorem to do some exercise, okay? So in this figure below, given AB equals CD, two segments are equal, angle BAC equals angle DCA. Can you prove these two line segments are parallel? AD is parallel with DC. Again, I'll give you 1 minute to think about that, and we'll have a look at the solution together. So you need to use one of the testing theorems. to prove two lines are actually parallel with each other, right? Either the corresponding angles are equal, or alternate interior angles are equal, or the same side interior angles add up to 180 degrees. Okay, have we finished? Alright, let's have a look at the solution together. So if you want to prove AD is parallel with BC, then as I said, you need to use one of the testing theorems, right? For example, if you can prove angle ACB equals angle CAD, then we can prove these two lines are parallel with each other, because these two angles are the alternate interior angles of these two lines with a passing line here, right? So how do you prove these two angles are equal? Note that triangle ABC and triangle ADC share the same side here, and also AB equals DC, and the angle in between are also equal, right? BAC equals DCA. So basically we can prove triangle ABC is congruent with triangle CDA, right? Therefore, the corresponding parts are also congruent. Therefore, you can prove this angle equals that angle, right? So how do you write that? So to write that in a mathematical language, you need to do it like this. First of all, because AB equals CD, AC equals CA, also angle BAC equals angle DCA. We have triangle ABC is congruent with triangle CDA, right? So usually you'll put the theorem you're using to prove these two triangles are congruent. So the theorem we are using here is called SAS, right? So this is read as triangle ABC is congruent with triangle CDA by SAS. Therefore, we know the corresponding parts are also congruent. The corresponding parts are angle ACB equals angle CAD, right? Well, these two angles are alternate interior angles. Alternate interior angles are equal, indicates these two lines or two line sections. AD is parallel with section BC, right? Yes?
We know that triangle ABC is congruent to triangle CDA, so it means that they are completely the same. Can't we just say that AD is parallel to BC because we don't, because we know that they're completely the same?
Completely the same does not indicate these two lines are parallel, right? I'll set an example. For example, this is triangle ADC. Well, this is your okay. This is triangle ADC. This is your AD, right? And for example, this is your triangle CBA. Then this is BC here. They are exactly the same, right? So can you see these two lines are parallel with each other? Not necessarily, right? You can say they are equal, but they are not necessarily parallel. Or for another example, ADC is here. So if you move this line to this side a little bit, this is A prime and then B, then C is here. These two triangles are also congruent, and this side is not parallel with this side, right? If you move this triangle to the right by a small angle here, right? So you can only say they are equal, but they are not necessarily parallel. So be careful with the logic here. All right, let's consider another example here. Okay, point E is the midpoint of both AC and BD as shown below. Can you prove that segment AB is parallel with segment CD? Okay, let's have a look at the solution together. So again, to prove lines are parallel, you need to refer to one of the 4 testing theorems, right? Remember, we have learned 4 of them, right? So you could either prove this angle equals that angle here, right? Or angle A equals angle C, because they are interior alternating angles. Interior alternating angles indicates parallel lines. So is this true? Of course, because we know this side equals this side equals this side, and these two angles are vertical angles. Vertical angles are congruent with each other, right? So you could say because AE equals CE, also BE equals DE, angle AEB equals angle CED. Again, SAS, right? Two sides and angle in between are equal. Therefore, we can conclude triangle ABE is congruent with triangle CDE. Remember, we need to write the corresponding vertices in the same order by the theorem SAS. Two sides and angle in between are congruent, indicating two congruent triangles. Therefore, we know the corresponding parts, angle B should equal angle D here, right? Therefore, if you have proved angle B equals angle D, interior alternating angles are equal, indicates segment AB is actually parallel with segment CD, right? Alright, next let's have a look at the second testing theorem we can use to prove two triangles are actually congruent, which is called SSS. So from the name, probably you can guess the meaning of this theorem. If each side of one triangle is congruent to the corresponding side of another, then the triangles are congruent. For example, in the figure on the left, if we can have AB equals XZ, AC equals XY, BC equals ZY, then we can say triangle ABC is congruent with triangle XZY by SSS. Again, you can try to prove this theorem, okay? We're not going to talk about the proof of this theorem in this class. You can try to do that by yourself after this class. once you have proved the first one, SAS, the remaining theorems are very easy to prove. Okay, so next let's have a look at some exercise questions we can use to practice using the theorem to solve questions. So first question here in series 1, I'll give you 2 minutes and then we'll have a look at the solution together. Okay, in this figure, the size and angle have measures as shown. Can you find angle MLN? Yes, Michelle?
Do we have to prove in this question?
You only need to prove when necessary. Well, I mean, in a test, if it's a short answer question, you need to briefly write your reasoning processes. Otherwise, if it's just a multiple choice, you can just select the correct answer. Or if it's a filling in the blanks question, just give the number is okay. But if it's a short answer, you should write your solution like this. So let's have a look at solution together, okay? So we can say because LO equals MN, ON equals LM, and LN equals LN. Of course, this is the parent, right? We have, by SSS, we have triangle LNO is congruent with triangle NLM. By SSS, three pairs of sides. Since angles MLN and angle ONL are corresponding parts of these two triangles, they must be equal, right? Therefore, we have angle MLN equals angle ONL, which is 25 degrees, right? Well, you don't need to write a lot of things. Just write the key statements to lead to your final conclusion. Okay, any questions? If not, let's consider another one here. In the figure below, like a kite, AD equals CD, AB equals BC. Can you prove that DB is perpendicular with AC? Okay, let's have a look at the solution together. You can prove it like this, because first of all, AD equals CD, AB equals CB, and DB equals DB, right? So first of all, we can prove the left triangle here is congruent with the right triangle here, right? We have triangle ADB is congruent with triangle CDB by SSS, right? Therefore, the corresponding angles are equal. ADE equals angle CDE. Then we can prove this triangle here is congruent with this one, right? Because they share the same side here. So you could write because AD equals CD and DE equals DE. They share the same side, which are equal apparently. And according to this, SAS, we can prove the triangle ADE is congruent with triangle CDE, right? Therefore, triangle ADE is congruent with triangle CDE by SAS, right? So here we are using both SSS and SAS. Therefore, the corresponding parts are equal, which means angle AED equals angle CED, which is 1/2 of 180 degrees, which is 90 degrees. Therefore, we have proved section DB is perpendicular with section AC, right? Any questions? Alright, if not, let's have a look at the next one. Can you prove that if the radius of a circle bisects or cut in half a chord of a circle that is not a diameter, then the radius must be perpendicular to the chord? Alright, so we can start with a diagram, drawing circle O. Let's call this circle O. Chord AB here, with midpoint M, and the radius through M. We then mark the equal pieces of the chord and equal radii of the circle. Connect AO and BO. So we know AO is the radius of that circle, BO is also radius of that circle, so AO equals BO. And because M is midpoint of AB, we have AM equals M, right? MB, sorry. And specifically, we have triangle AMO is congruent to triangle BMO by SSS. So we have angle AMO equals angle BMO. Also, since angle AMO plus angle BMO equals 180 degrees, then we know angle AMO equals angle BMO equals 90 degrees, right? Good, if no questions, let's have a look at the third theorem we can use. So the third testing theorem states that if two angles and the side between them in one triangle are congruent to the corresponding parts in another triangle, then the triangles are congruent. For example, if we have a pair of triangles here on the left, because angle B equals angle E, BC equals EF, angle C equals angle F, then we can conclude triangle ABC is congruent to triangle DEF. Again, I'm not gonna prove this for you. Try to prove this by yourself after this class, okay? And then this gives us the fourth testing theorem we can use, which is AAS, stating that if two angles and the side not between them in one triangle are congruent to the corresponding parts in another triangle, then the triangles are congruent. For example, if we have a pair of triangles here, if we have angle G equals angle J, angle F equals angle K, and FH equals KI, then we can conclude triangle FGH is congruent to triangle KJI by AAS. Be clear? So there are 4 testing theorems we can use to determine if 2 triangles are congruent. Also, note that when using AAS, the equal sides must be adjacent to corresponding equal angles. For example, the angles shown below are not congruent because the equal sides are not adjacent to the corresponding equal angles. So be careful when you use AAS. Alright? Alright, if no questions, let's have a look at an example. So in the figure on the right, if given PQ equals PR and PQY equals angle PRX, can you prove QY equals RX and XN equals YN? I'll give you 2 minutes to think about this, and after that we'll have a look at the solution together, okay? Alright, let's have a look at the solution together. In question A, well, we are given angle PQY equals angle PRX. And of course, we also know angle P equals angle P and PQ equals PR, right? This is given information. Then we have triangle PQY must be congruent to triangle PRX by ASA congruence, right? Therefore, the corresponding parts are also congruent, so QY equals RX. So the proof is done. And in question B, you can start by using triangle PQY is congruent to triangle PRX. We have proved this in question A. Then we know the corresponding parts are also congruent, so PY equals PX. And because we also have PR equals PQ, YR equals XQ, and because angle Q equals angle R, angle XNQ equals angle YNR. Therefore, we have triangle XNQ must be congruent to triangle YNR by AAS congruence, right? And therefore, the corresponding parts are also congruent. We can prove XN equals YN. Okay, have a look at the solution here. Any questions, just let me know, okay? Alright, so if you don't have any questions, let's make a brief summary. So we can use the following 4 testing theorems to determine if 2 triangles are congruent. They are SSS, SAS, ASA, and AAS. Are you clear?
Yeah.
Also,
so does I was a quick question. So does the proof ASS not exist if you have 2 sides and another angle?
ASS, right?
Yeah.
Yes, I'm just gonna mention this. So also be careful that ASS or AAA does not necessarily mean congruence, because if you consider this 2 triangles here, this little triangle and the larger one here, they share the same angle A, right? And they share the same side here. And suppose this side equals this side. So this is ASS, right? But apparently these 2 triangles are not congruent. Can you see that?
Yeah.
So ASS does not necessarily mean congruence. Also AAA neither. Because if you consider the larger one and the smaller one here, corresponding sides are parallel, which means we have 3 pairs of congruent angles, but apparently the larger triangle is not congruent with the little triangle here, right? Okay, So ASS or AAA does not necessarily mean congruence. Are you clear?
Yes.
Alright, then next let's have a look at the concept of isosceles triangles. So if a triangle has at least two equal sides, then this triangle is called an isosceles triangle. In an isosceles triangle that has exactly two equal sides, the equal sides are called legs, and the third side is called base. As shown in this diagram, the angle included by the legs is called the vertex angle. And angles that have the base as one of their sides are called base angles. So this is a base angle. This is another base angle. Are you clear?
Yeah.
Okay, so if you're clear with the concept of isosceles triangles, next let's have a look at the properties of isosceles triangles. First, if a triangle is an isosceles triangle, then the two base angles are equal. For example, given triangle ABC and AB equals AC, so this is an isosceles triangle with AB equals AC. Can you prove that angle B equals angle C? Alright, so actually we can connect, I'll give you a quick proof here. We can connect A to a point P on segment BC such that BP equals CP. This is possible, right? And because AB equals AC, AP equals AB, BP equals CP, we have triangle ABP must be congruent to triangle ACP by SSS, right? And therefore we can prove angle B equals angle C. Therefore, we have the first property of isosceles triangle. If a triangle is isosceles triangle, we know the two base angles are equal. Any questions? Okay.
No.
If no questions, let's see the second one, which means if at least two interior angles of triangle are equal, this triangle is an isosceles triangle, and such two interior angles are its base angles. Well, also we can actually prove this property. For example, given triangle ABC here, and angle B equals angle C, can we prove AB equals AC? So I'll just give you the proof here because it's very straightforward. Okay, we can do it like this. Again, we can connect point A to point P on segment BC such that AP is perpendicular to BC. This is also doable, right? And because angle ABP equals angle APC, angle B equals angle C, AP equals AP, we have triangle ABP must be congruent to triangle ACP by AAS, right? And therefore we can prove corresponding parts are also congruent. So AB equals AC, right? So in conclusion, if at least two interior angles of a triangle are equal, this triangle is an isosceles triangle, and such two interior angles are its base angles. Okay, clear? Okay, and let's see the third property of an isosceles triangle, which states that if a triangle is an isosceles triangle, then the following sections coincide. First, the height on the base. Second, the bisector of the vertex angle. Third, the bisector of the base. For example, given triangle ABC, AB equals AC, AD is perpendicular to BC, we can actually prove first angle BAD equals angle CAD, and segment BD equals segment CD, right? Because I'll give you a quick proof here. AD is perpendicular to BC, then we know this angle and this angle are both 90 degrees, right? And because AB equals AC, this is given information, and they share the same length AD, right? Oh, sorry. We should use angle B equals angle C. So by AAS, we know triangle ABD is congruent to triangle ADC, right? Then we can prove angle BAD equals angle CAD, and also BD equals CD, right? Are you clear?
Yeah.
Okay, so we have learned 3 important properties of isosceles triangle. So next, let's have a look at the concept of equilateral triangles. A triangle with all sides equal is called an equilateral triangle, and an equilateral triangle is a special case of isosceles triangle, right? Because it's also a isosceles triangle which has 3 internal angles be 60 degrees. And because an equilateral triangle is also a special case of isosceles triangle, it will have all the properties we have learned. Moreover, each of the interior angles of an equilateral triangle is 60 degrees, right? And vice versa. So if you can prove a triangle has 3 internal angles with 60 degrees, then this triangle is actually an equilateral triangle, right? Also note that the triangle with no sides equal has its own name, which is called a scalene triangle. Are you clear?
Yeah.
Alright, good. Then let's have a look at some practices. So first, in the diagram on the right, if AC equals CD equals DB, and angle B equals 23 degrees, can you find the measurement of angle A? Again, I'll give you 2 minutes to think about this problem, and then we'll have a look at the solution, okay? If you finish earlier, just let me know. Alright, first, because CD equals BD, then we know angle BCD equals angle CBD equals 23 degrees, right? And angle ADC equals angle BCD plus angle CBD, which is 46 degrees. And because AC equals DC, we have angle A equals angle ADC, which is 46 degrees, right? Any questions?
No.
Okay, then let's consider another quiz. In the diagram on the right, O is the center of the circle. We have AB is parallel to CD, angle ABO is 24 degrees, and angle OBC equals angle OCD. Can you find angle BOC? Again, I'll give you 2 minutes to think about this problem, okay? Alright, let's see the solution together. So, because OB equals OC, which are the radius of that circle, we have angle OBC must equal angle OCB, right? And in order to facilitate our discussion, we let the desired angle be x. So we let the desired angle BOC be x. We have angle OBC equals angle OCB equals angle OCD, which is a half of 180 degrees minus x, right? And because AB is parallel to CD. We have angle ABO plus angle OBC plus angle OCB plus angle OCD equals 180 degrees, right? And therefore 24 degrees plus 3 half of 180 minus x equals 180 degrees. And this gives you one equation in terms of unknown variable x, in which we can solve x is actually 76 degrees, right? So have a look at the solution here. Let me know if you finish, okay? Alright, so that concludes topic 3, congruent triangles. I'll give you some more practices when we finish today's lesson, okay? And next, let's have a look at topic 4, perimeter and area. Okay, first the concept of a perimeter. Perimeter of a closed figure is how far you travel if you walk along its boundary, but all the way around it once. So the perimeter of a triangle is simply the sum of the lengths of the sides of that triangle. Very clear? It's a very straightforward concept, right? So let's have a look at an example here. A triangle ABC is equilateral, then find AB given that the perimeter of triangle ABC is 36. Again, because this exercise is pretty straightforward, we'll have a look at the solution together. So since triangle ABC is equilateral, all of its sides are equal, right? So if we let each have length S, then we have 3S equals 36, so S equals 12, right? And therefore we know AB equals 12. Any questions?
No.
Okay. Let's consider another question here. Given a diagram like this, can you find the perimeter of triangle DEF? Okay, let me know if you finish, okay? Alright.
I finished.
Okay, so here we have angle E equals angle F. Then we have DE equals DF, which is 8. Therefore, our parameter is DE plus DF plus EF. So that's 16 plus 8 square root 3, right? Also a very straightforward question. And then let's consider another one. In the diagram below, if xy equals 5 square root 2, yz equals 10, and angle y equals angle z, which are both 45 degrees, can you find the perimeter of triangle xyz? Again, very straightforward question, right? Because this is also a isosceles triangle, xz equals xy, which is also 5 square root 2, so the perimeter is just a 10 plus twice of 5 square root 2, which is 10 square root 2, right?
Yeah.
Okay, then let's consider another one. So how about this one? Triangles ABC, ADE, and EFG below are all equilateral. Points D and G are midpoints of AC and AE, respectively. If AB equals 4, what is the parameter of figure ABCDEFG? Again, let me know if you finish, okay? Alright. Since D is the midpoint of AC, equilateral AD has that length AB over 2, which is 2, right? And since G is the midpoint of AE, equilateral triangle EFG has side length AE over 2, which is 1, right? Then the parameter of figure ABCDFG is AB plus BC plus CD plus DE plus EF plus FG plus GA. And this gives us 4 plus 4 plus 2 plus 2 plus 1 plus 1 plus 1, which is 15, right? You have any questions?
Nope.
Alright, then let's consider another one. Another quick quiz. A triangle with parameter 45 has one side that is twice as long as the shortest side and another side that is 50 longer than the shortest side. Can you find the length of the shortest side of the triangle? Okay, let's have a look at the solution together. So we can actually let the shortest side be x, right? Let the shortest side have length x, and we want to solve x. Then the other two sides have length 1.5x and 2x. We know the parameter of the triangle is 45, so 45 equals x plus 1.5x plus 2x. Again, we have one equation and one unknown variable x, so we can solve x. So basically we have 4.5x equals 45, and this gives us x equals 10, right? So the shortest side of that triangle has length 10. Any questions?
Nope.
Okay, so this is pretty much about concept of perimeter, which is pretty straightforward. And next, let's have a look at area. The area is a measure of a region's size on a surface. Roughly speaking, the area of a figure is the total number of 1 by 1 squares needed to cover that figure, where we add fractional squares when we only need a piece of square to do the job. For example, we need 3 plus a half of squares to cover the region ABCDF at right. So we see the area ABCDF is 3 plus 1/2. We will often use brackets to denote the area. For example, if you want to denote the area of ABCDF, you should use this symbol here. Are you clear? So
Yes.
let's have a look at some examples. We call a four-sided figure with 4 right angles a rectangle, and we know the area of a rectangle is consecutive sides of lengths L and W is L by W. So in the figure on the left, the area of that rectangle is 4 by 5, which is 20, right? It's a pretty straightforward concept. And of course, the area of the right triangle is a half of the corresponding rectangle, which is a half of base times height, which is, in this case, on the left, a half by 6 by 4, which is 12, right? Are you clear?
Yes.
Okay, then let's consider another quick quiz. Can you find the area of triangle DEF given that J is on segment EF and DJ equals 8, DJ is perpendicular to EF, and EF equals 7. So according to what we have learned here, you know the base and you know the altitude, so the area of triangle DEF can be calculated by a half of the base and the altitude or height, which is 28, right? Any questions?
No.
Okay, Then another quick quiz, which is also pretty straightforward. Given angle ZXY equals angle XWY equals 90 degrees, XY equals 8, XZ equals 6, and ZY equals 10. Can you find XW? So note that XW is altitude on the side ZY. Let me know if you finish, okay?
No, I'm done.
Okay.
Yeah.
So we can actually use the area of that triangle as a handler. So we know the area of the triangle XYZ can be calculated by half of XY and XZ. Can also be calculated by 1/2 of base ZY times XW. Therefore, we have XY times XZ equals ZY times XW. That means XW equals XY times XZ over ZY. And this gives us XY is 8, XZ is 6, ZY is 10. So that's 24 over 5, right? Is it clear?
Yes.
Okay, then let's consider another one. In the diagram on the right, KO equals 6. Also, KO is perpendicular to OM. LM equals 7. And KM equals 12. Can you find the area of triangle KLM and find the length of LN? Okay, I'll just give you the solution. Because again, this is a pretty straightforward question, right? So OK is the altitude on the base LM. So for the first question, the area of triangle KLM equals 1/2 of the base LM times corresponding altitude or height, OK, right? So that's 1/2 of 7 by 6, which is 21, right? You follow me?
Yeah.
Also, we know the area of triangle KLM can be calculated by 1/2 of KM corresponding height LN. Therefore, we know LN equals twice of the area of that triangle over KM. So that gives us 2 by 21 over KM, which is 12. And that's 7 over 2, right?
Yes.
Okay. Okay, again, if you don't have any question, let's consider the next one. A square poster is replaced by a rectangular poster that's 2 inches wider and 2 inches shorter. What is the difference in the number of square inches between the area of the larger poster and the smaller poster? Yeah, let me know if you finish, okay? Alright, so originally we have a square poster and we could let the side of the square poster be x. Therefore, the area of the square poster is just x squared, right? And the area of the rectangular poster is given by the product of the height and width, which is x plus 2 times x minus 2, right? Can you follow me? And this can be simplified to x squared by 4. Therefore, you can see that the area is reduced by 4 square inches, right? So difference is 4 square inches. Any questions?
Yeah, no question.
Okay. Alright, next let's have a look at the concept of same base or same altitude. So if two triangles share an altitude, then the ratio of their area is actually the ratio of the bases to which that altitude is drawn, right? This is particularly useful in problems in which two triangles have bases along the same line. Second, if two triangles share the same base, then the ratio of their areas is the ratio of the altitudes to that base. This is apparent because area of the triangle equals half of the height or altitude times corresponding base, right? So let's see an exercise to illustrate the concept here. So given that BC equals 40 and CD equals 20 in the figure, what are the ratios of area of triangle ABC over ACD and the ratio of area ABC over area of triangle ABD? So we know the altitude from A is the same for both triangle ACD and ABC, right? If you let H be the length of this altitude, hence triangle ABC is calculated by half of BC times H. So suppose this is H. And triangle ACD can be calculated by half of CD times H, right? Therefore, we know the area of triangle ABC over the area of triangle ACD is given by BC over CD. And this is actually 2, right? And similarly, the altitude from A in each of triangle ABC and triangle ABD has length H. Therefore, we also know the ratio of area ABC and area of ABD equals half of BC times H, half of BD times H. So that equals BC over BD, right? And we know that's 40 over 60, which gives us 2 over 3. Are you clear?
Quick question. So, I know that.
Okay, consider this problem here and let me know if you finish, okay? Okay, let me give you some hints. Because triangle ABX and triangle CBX share an altitude from point B. Then we have AX over B over CX should equal the area of ABX over the area of CBX. So this gives us 8 over 5, right? Also, triangle ADX and triangle CDX share an altitude from D. Then we have the area of ADX over the area of CDX should equal AX over CX, which is also 8 over 5, right? So can you find the area of triangle ADX now? So we know the area of triangle ADX should equal A over 5 times the area of CDX, right? Can you follow me? Which is 16. Okay, have a look at the solution here. Let me know if you finish, okay? Alright, good. Then let's consider another one. Here in the diagram below, PT equals 6. TR equals 3. QE equals 4. Can you find the area of PQR, PTQ, and QTR? Then find the ratio of TR over PT and area of QTR over PTQ. Again, let me know if you finish, okay? Alright.
Yeah, I finished.
Okay, so let's have a look at the solution. So the area of PQR is a half of base times corresponding altitude or height, which is a half of 9 by 4, and this is 18, right? And then PTQ is a half of PT times QE, which is 1/2 of 6 by 4, and this is 12, right? And the area of QTR is a half of TR times QV, and this is half of 3 by 4, which is 6, right? And in question B, first of all, we have TR over PT is 3 over 6, which is 1 over 2, right? And the ratio of the two areas, QTR and PTQ, is given by actually TR over PT. So it's also 1 over 2, right? Any questions?
Nope.
Okay, then let's consider another one. So how about this one? We are given a diagram below, and AB equals 2, BE equals 3. Can you find the following ratios? A, B, and C. Okay, let me know if you finished, okay? Alright, let's have a look at the solution. This first one is pretty easy. BCD and ACD share the same base, CD. So the ratio of the two area is given by the altitude to the same base. So BE over AE. This is 3 over 5, right? Second question, the area of ADBC over the area of ADC is given by, okay, first of all, ADBC is the area of ACD subtracted by the area of BCD over the area of ADC is actually ACD, right? So this is given by 1 minus the ratio between BCD and ACD, which is already calculated in the previous question. So this is 2 over 5. For the third question, the area of BCD over the area of ACBD. So note that ACBD is this area here. So we can rewrite that to 1 over the area of ACBD over the area of BCD. So the advantage to write it like this is then we can calculate area of ACBD by using ACD subtracted by BCD. Then over the area of BCD. So this is given by the area of ACD over the area of BCD minus 1, right? So that's 1 over 5 over 3 minus 1, and eventually we have 3 over 2. Did you get it? Any questions?
No questions.
Alright, then let's consider another quick quiz. So if you are given a diagram like this, can you find Qx in diagram at right? Given Wx equals 8, And area PQX is a sixth of the area of WXYZ. Okay, I'll give you 2 minutes to think about this question.
16/3?
It's actually 16/3.
Oh.
Okay, we can have a look at the solution together. So first of all, we know the area of WXYZ can be calculated by WX by YX, right? And this is actually WX by twice of PX, right? And the area of PQX is given by half of QX by PX, and this is 1/6 of the area of WXYZ, and therefore this is 1/6 times WX by 2PX, and therefore we can simplify this to, well, if you consider this expression and this expression here, they are actually equal, right? So this gives us half of QX equals 1/6 of WX by 2. And therefore we know QX equals 2/3 times WX, which is 2/3 by 8, which is 16/3, right? Okay, let me know if you finish, okay?
No questions.
Alright, then actually there are a number of other questions, but because of time constraints, I'll leave these questions to you after this class. You can treat this as a homework, okay?
Sure.
Alright, then let's turn to the next topic of today's lesson. We'll complete topic 5 as well. Topic 5 is about similar triangles. Okay, so first of all, let's have a look at the concept of similar figures. Two figures are similar if one is simply a blown up or possibly rotated and or flipped version of the other. Corresponding angles in similar figures are equal, and the ratio of the lengths of corresponding sides of similar triangles is always the same. For example, in similar quadrilaterals ABCD and EHGF, we have corresponding angles are congruent, so angle A equals angle E, angle B equals angle H, angle C equals angle G, angle D equals angle F. Corresponding sides are proportional, so we also have the following ratios are all equal. Also, we denote these figures as similar by writing ABCD is similar to EHGF. We'll use this notation here to denote these two figures are similar. Are you clear?
Yes.
Okay, let's consider a quick quiz here. Given that triangle ABC is similar to triangle YXZ, which of the statements below must be true? Okay, I'll give you some visual aids. Suppose this is a triangle ABC, another triangle YXZ. Which of these statements below must be true? Let me know if you finish, okay?
I think A, B, and
A is
E
true.
are true.
B is true, right?
Yeah, and E.
E? Well, actually, D is true. E is not necessarily true. Okay, let's have a look at the solution together. So if triangle ABC is similar to triangle YXZ, then we have corresponding sides are proportional. So we have AB over YX equals AC over YZ equals BC over XZ, right? So it follows that AB over BC equals YX over XZ. And also we have AC times YX equals AB times YZ, right? Hence AB over YX equals AC over YZ is true. So the first one is true, right? From part A, we know that AB over BC equals YX over XZ is also true. So the second one is also true. So from part A, we know that the third one is not necessarily true, right? And from part A, also note that AC times YX equals YZ times BA must be true because we have proved it here, right? So D is correct, D is always true, but E is not necessarily true. So only A, B, and D must be true. Can you follow me?
Okay, I see.
Alright, then let's consider another quiz. If triangle ABC is similar to another triangle ADB, AC equals 4 and AD equals 9, what is AB? Okay, remember when you write similar triangles, we write corresponding vertices in the same order. So if triangles ABC and ADB are similar, then corresponding sides must be proportional. So we have AB over AD should equal AC over AB, right?
Yeah.
Then we have an equation in terms of AB. So AB squared should equal AC times AD. We know the length of AC and AD. So AC equals 4, AD equals 9. Therefore, we know AB is a positive 6 because length of a side cannot be negative. Therefore, we know AB equals 6, right? Any questions?
Give me a second, I'm just gonna jump this thing.
Alright, now the problem is how do we determine if two triangles are similar? Again, we have a series of testing theorem can use. The first one is called AA similarity, which states that if two angles of one triangle equal two angles of another, then the triangles are similar. For example, let's look at the diagram below. If you can have angle A equals angle B, angle B equals angle E together, then this implies these two triangles ABC is similar to triangle DEF. So corresponding sides are proportional. AB over DE equals AC over DF equals BC over EF. So this is called AA similarity. Very clear?
Yes.
So the problem is, can you prove the AA similarity is actually true? Can you prove this theorem? In other words, given if you have a diagram like this, given angle ABE equals angle ACD, also note they share the same angle A. Can you prove triangle ABE is similar to triangle ACD? let's do this together. It can be done like this. So first of all, it's obvious that corresponding angles are equal, right? Because they share the same angle A, and it's given that ABE equals angle ACD, right? So first of all, it's obvious that the corresponding angles are equal, which means angle BAE equals angle CAD, angle ABE equals angle ACD, and also angle AEB equals angle ADC. And then we can draw segment CE and segment BD. Connect C and E. Connect B and D. And because we have the ratio of the area of ABE over the area of ACE equals AB over AC. Can you follow me? Because it shares the same altitude from point E, right? And also we have this ratio between the area of ABE over the ratio ABD equals AE over AD. And also because the area of BCE equals the area of BDE. Well, this indicates that the area of ACE equals the area of ABD, right? And then we have the ratio between AB over AC should equal the ratio of AE over AD. And therefore we know AB over BC should equal AE over ED. And if we let AB equals A, BC equals B, and AE equals A times a coefficient K, then we have ED equals B times K, right? Of course, K belongs to the real number set and K is not 0. Then we could draw segment EF, which is parallel to segment AC. So here. This is doable, right? Use the same method, we can prove So use a similar method, we can prove actually ED over AE should equal DF over CF, which is also the ratio between B and A, right? Then if we let DF equals BM, then we have CF equals AM, right? Where M belongs to the real number set, again M is not 0. Because BE is parallel to CF and BC is parallel to EF, we have BE equals CF equals AM, right? Okay, I'll write it on top left here. And therefore we know BE over CD should equal AM over AM plus BM, which gives us A over A plus B, right? Which also equals AB over AC, which equals AE over AD. You see that? Therefore, we have proved the corresponding angles are equal, corresponding sides are proportional. Then we can conclude triangle ABE is similar to triangle ACD. So I'll put it here, okay? So have a look at the proof here and let me know if you finished, okay? So we can use this method to prove AA similarity theorem is actually true. So next time you want to determine if two triangles are similar, you can use AA similarity to show if two triangles are similar.
Yeah, you can, yeah, ask that.
Alright, then let's move on. Then let's consider a exercise here. In the figure right, if MN is parallel to OP and OP is 12, MO is 10, LM is 5, can you find the length of MN? So we can make use of the pair of similar triangles, right?
Yeah.
So because we have a pair of parallel lines, this angle equals this angle, they share the same angle L here, so we know triangle LMN is similar to triangle LOP by AA similarity. Then we have LM over LO equals MN over OP. And since LO equals LM plus MO, which is 15, we now have 5 over 15 equals MN over OP, which is 12. And this gives us MN equals 4, right? A pretty straightforward question. Any questions?
No questions.
Okay, then let's consider another one. Lengths in the diagram are marked and WX is parallel to YZ. Can you find PY and WX? Have you finished? Okay, let's have a look at solution together. Because we have WX is parallel to YZ, then we have angle W equals angle Z and angle X equals angle Y. Therefore, we have triangle WPX is similar to triangle ZPY, right? Hence, we have PX over PY equals WX over YZ equals WP over PZ. Substitution gives us 3 over PY equals WX over 12 equals 5 over 10. Therefore, we can easily find PY equals 6 and WX equals 6. right? Any questions?
Yeah.
Okay, and there are a number of other questions. Because of the time constraints, I'll leave these questions for you to solve after this class. Okay, you can use them as a homework. And the second theorem we can use to determine if two triangles are similar is called SAS similarity, which tells us that if two sides in one triangle are in the same ratio as two sides in another triangle, for example, in this diagram, as AB over AC equals D over DF below, and the angles between these sides are equal, as shown here, angle A equals angle D, then the triangles are similar. Note that we can also write the ratio equally as the ratio of corresponding sides in the triangle. So you could also write AB over DE equals AC over DF. So this is called SAS similarity. Are you clear?
Yeah, SAS got it.
And actually, we can also prove the SAS similarity like this. So let's consider this problem here. Given AB over AC equals AE over AD, we can actually prove these two triangles are similar using this method here. So I'll just give you the proof here. So first of all, we can draw the segment BF parallel to CD and intersect with segment AD at point F. So let's say draw BF parallel to CD. This is doable using straight edge and compass construction. Then we know that angle ABF should equal angle ACD, right? And because angle BAF equals angle CAD, we know triangle ABF must be similar to triangle ACD by AA similarity, which we have already proved. Therefore, we know AB over AC should equal AF over AD. And therefore, AF should equal AB times AD over AC. And because AB over AC equals AE over AD, this is given information. Then we know AE can also be expressed as AB times AD over AC. The length of AF equals the length of AE. This means F and E are actually the same points, right? So if F and E are the same points, then we know triangle ABE is similar to triangle ACD. You get it?
Yeah.
Okay. So,
Let me just screenshot this real quick. Yeah.
all right. Then if no questions, let's do a quick exercise like this. Given AC equals 4, CD equals 5, AB equals 6. Can you find BC if the parameter of BCD is 20? Okay, I'll give you some hints. So we know the length of three sides. And also note that AC over AB is 2 over 3. AB over AD is also 2 over 3. And they share the same angle A, right? So what does this tell you? This tells you triangle ACB is similar to triangle ABD by SAS, right? Which we have just learned. And also, since the sides of triangle ABD are 3/2 of the corresponding sides of triangle ACB, we have BD equals 3/2 times BC. Now we can use the parameter information. We know that BC plus CD plus DB equals 20. Then we have BC plus 5 plus 3/2 BC equals 20. Therefore, we can solve. BC is actually 6. Okay, have a look at the solution here. Let me know if you have any question. Okay.
So AB is 6. Oh yeah, okay. I think.
All right. Then there is another question. You can use this as a homework as well. And then the third theorem you can use to determine whether two triangles are similar is called SSS similarity, which says that if each side of one triangle is same constant multiple of the corresponding side of another triangle, then the triangles are similar, and therefore their corresponding angles are also equal. So, for example, consider these two diagrams. We have AB over DE equals AC over DF equals BC over EF. So we can conclude triangle ABC is similar to triangle DF by SSS similarity. Are you clear?
Yeah.
Okay, also we can actually prove SS similarity is true. So consider this question by yourself. Given two triangles and AB over PQ, BC over QR, AC over PR are all the same ratio, can you prove triangle ABC is similar to triangle PQR? So I'm not gonna write the proof here for you, so consider this as a homework as well, okay? If you have any questions, just let me know, probably in our next class, okay? Try to prove this by yourself. It's not that complex. And use the so let's make a summary here. So if you want to determine if two triangles are similar, then you could use AA similarity or SAS similarity or SSS similarity. There are 3 testing theorems you can use, right? Are you clear?
Yep, 2 testing theorems. Got it.
Okay, and again, because of the time constraints, there are some other exercises. I'll leave them as the homework for you. And now let's consider some other related concepts here. So if BC is parallel to DE and BD and CE meet at A as shown on the right, then we also have the following relationship: AB over BD equals AC over CE. Also try to prove this at home, see if you can have the same conclusion here. If two triangles are similar such that the sides of the larger triangle are k times the size of the smaller, then the area of the larger triangle is k squared times that of the smaller. This relationship holds for any pair of similar figures, not just for triangles. Are you clear?
Yep. Yeah, I think
Alright, so these are the 2 other related concepts to similar triangles. And last, let's consider one last exercise, then we can conclude today's lesson. So given triangle ABC similar to triangle YZX, the area of triangle ABC is 40, area of triangle YZX is 360, AB equals 9, BC equals 12. Can you find the following? A, the length of YZ. B, the length of the altitude to side XZ of triangle YZX. So I'll give you 3 minutes to have a look at this question here, and then we'll have a look at the solution together, okay? Alright, let's have a look at the solution together. First question, since triangle ABC is similar to triangle YZX, and the area of YZX is 9 times the area of triangle ABC. Then we know the side length of the triangle YZX over the side length, corresponding side length of triangle ABC equals square root of 9, which is 3, right? And therefore we know YZ should equal 3AB, which equals 27. Can you follow me?
Yep.
Where the order of the vertices in the triangle similarity relationship tells us which side of triangle ABC corresponds to YZ in triangle YZX. For second question, by the same reasoning as part A, we have XZ equals 3BC equals 36. Letting our desired altitude have length h, to facilitate our discussion, then we have the area of triangle YZX equals a half of XZ times corresponding altitude h. Since we are given the area of triangle YZX equals 360, then we have h times, so half of h times XZ equals 360. And because XZ equals 36, then we have h must equal 20, right? Can you follow me?
Yeah. Yeah.
Okay, so that's pretty much about today's lesson. Hold on, let me give you today's homework, okay? Some of the homework questions are actually from the ACM 10. So if you want to prepare for the ACM 10, it's better for you to complete all the homework. Okay, you can try to finish as much as possible to see if you can solve each of the questions. Okay, let me see. Okay, first one. Okay, please receive the files in the chat box. Okay, first one is the homework of topic 3, congruent triangles. Second file is homework of perimeter and area. Topic 4. And the third file is homework of topic 5, similar triangles. Have you received them all?
I'm downloading topic 4 and topic 5 right now.
And topic 1, 2 homework are also given to you in the previous lesson, right?
Yeah, so I have them now.
Yeah, if you have the time, it's better to have a look at all the questions. Okay, let me know if you finish, okay?
Okay, well, I've downloaded all 3 of them. So once I have them downloaded, do I like?
Have you finished?
Yeah.
Okay, so I'll see you next time then, alright?
Alright, see you.
Okay, see you.
Thank
Bye.
you though. Bye.
Bye.